Let's start this explainer with a doomsday scenario. Imagine, just for a second, that humanity is facing total annihilation from some crazy environmental disaster, and literally all of our scientific knowledge is about to be wiped out. If you could pass exactly one sentence onto the next generation of creatures in the universe to help them rebuild, what would it be? It's a huge question, right? But the answer actually reveals an absolute core secret of our universe, and it's the exact foundation of the hidden, chaotic world we're diving into today. Well, the legendary 20th century physicist Richard Feynman actually answered that exact doomsday question, and he pointed straight to the atomic hypothesis. He truly believed it's the single most vital piece of knowledge humanity possesses. That one simple sentence, that all things are made of atoms, little particles moving around in perpetual motion, attracting and repelling each other, that is the master key to unlocking the physics of everything around us. So here's our game plan for today. We'll start with the atomic hypothesis, then move into the behavior of gases, crack open the kinetic theory of gases, figure out what temperature actually is, and wrap up with energy and motion. Let's get into it. Section 1. The atomic hypothesis. You know, it's honestly amazing that ancient scholars imagined the existence of atoms centuries before they could ever actually see them. Back in the 6th century BC in India, Kanada argued that if you kept subdividing matter forever, eventually there'd be no difference between a tiny mustard seed and a massive mountain. He called that incredibly tiny smallest particle Parmanu. Around the same time over in Greece, Democritus coined the term atom, which literally means indivisible. But it wasn't until the 19th century that folks like John Dalton gave us the formal scientific atomic theory, and Avogadro realized that equal volumes of gases actually hold the exact same number of molecules. Now, when we talk about gases, we really have to talk about spacing, because gases are delightfully roomy compared to tightly packed solids or flowing liquids. I mean, the size of a single atom is about an angstrom, that's 10 to the negative 10 meters. In solids and liquids, those atoms are packed incredibly tight, just a couple of angstroms apart, locked in by strong forces. But gases? Those atoms are tens of thousands of angstroms apart. They're just so much freer. And because gas atoms are so incredibly spread out, they aren't constantly tugging on each other like atoms in a solid do. Instead, these zoom across these huge microscopic distances in a totally straight line before finally bumping into a friend. We call that average distance the mean free path. And it's exactly because of this, the fact that the static, calm appearance of a gas is actually a total illusion hiding this flurry of rapid dynamic collisions, that their behavior is surprisingly simple to study.
Section 2. The behavior of gases.
To make the math actually workable, physicists dreamed up this concept of the ideal gas. It's a theoretical model. We essentially pretend the molecules are so wildly far apart that they completely ignore each other until the exact moment they collide. No complex long-range attractions, just tiny, perfectly elastic billiard balls zipping around. And making that assumption lets us use the beautiful equation, pressure times volume equals the number of moles times the universal gas constant times temperature. Now, obviously, no real gas is absolutely 100% ideal, but real gases do get really close to this perfect ideal behavior when they're at low pressure and high temperatures. Why? Well, because with a lot of heat and plenty of empty space to roam freely, they're moving so incredibly fast and are so spread out that their interactions really are practically negligible. And Boyle's law falls right out of this ideal gas model. If you take a gas and keep its temperature exactly the same, but you squish that given mass of gas down into a tiny volume, the pressure shoots way, way up. They're inversely proportional. Less space simply means way more frequent collisions against the walls of whatever container it's in. Okay, prepare to have your mind blown for a second by the sheer scale of what we're talking about. 6.02 times 10 to the 23rd power. This is Avogadro's number. If you take just 22.4 liters of any ideal gas, standard temperature and pressure, so roughly the size of a normal party balloon, it holds exactly that many molecules. That is an unimaginably gigantic quantity of microscopic particles zipping around inside that balloon right now. Section 3. Kinetic Theory of Gases. Let's look at just a single one of those molecules inside a cubic container. As it zooms along and hits the wall, because we assume the collision is perfectly elastic, it bounces off with the exact same speed, just going in the opposite direction. So its momentum in the x direction fully reverses. And that tiny difference in momentum means a really, really minuscule amount of force is physically transferred from the molecule directly to the wall. I mean, sure, one molecule hitting a wall doesn't really do much, but remember Avogadro's number? When you have billions upon trillions of these incessant microscopic collisions happening every fraction of a millisecond, the math adds up fast. Every single bounce transfers a tiny bit of momentum. That total momentum transfer over time creates a steady microscopic force. And when you spread that force over the total area of the wall, that is exactly what we macroscopically feel and measure as gas pressure. Pressure is quite literally just millions of tiny atomic hammer strikes.
Section 4. What is temperature really?
To really answer this, let's use a brilliant analogy. Imagine the legendary cricket player Sachin Tendulkar holding his incredibly heavy bat. If a ball hits that bat while he's holding it perfectly still, it just bounces off. But what if he's actively swinging that massive bat directly towards the ball? Think about it. Does the ball rebound faster or slower after that collision? It rebounds way faster, right? The moving bat physically transfers energy into the ball. Now, let's apply this straight to a cylinder filled with gas. The gas molecules are our cricket balls. If you push a heavy piston down into that cylinder to compress the gas, that piston acts exactly like Tendulkar's moving bat. As it pushes in, it literally smacks into those gas molecules, drastically increasing their rebound speed. They move faster. And here is the absolute game changer. That increased microscopic kinetic energy is literally exactly what we observe as a rise in temperature.
Just to give you an idea of how fast these tiny cricket balls are actually moving, at a cozy 300 Kelvin, which is roughly room temperature, a single nitrogen molecule is zooming around the room you're sitting in at a root mean square speed of 516 meters per second. That's basically the speed of sound. They are moving incredibly fast, constantly colliding, and that kinetic energy is literally the temperature of your room.
Section 5. Energy and motion. This elegant little equation is the absolute heart of the kinetic theory. E equals 3/2 kBT. E is the average translational kinetic energy of a molecule, T is the absolute temperature, and Kb is the Boltzmann constant, which beautifully links our macroscopic, everyday world to the microscopic one. This tells us definitively that temperature is simply a direct measurement of average molecular kinetic energy. It doesn't matter what the pressure is, it doesn't matter what the volume is, and it doesn't even matter what kind of gas it is. If two completely different gases are at the exact same temperature, their molecules have the exact same average kinetic energy, period. And this concept has some pretty massive real-world applications. For instance, when nuclear scientists enrich uranium to separate the lighter U-235 isotope from the heavier U-238, they rely completely on this kinetic behavior. If both are mixed as a gas at the same temperature, their average kinetic energy is identical. But since kinetic energy is 1/2 mass times velocity squared, the lighter U-235 molecule absolutely has to be moving just a tiny bit faster to maintain that equal energy. And because it's moving faster, it actually leaks through a highly specialized porous wall just a fraction quicker than the slower, heavier U-238. As we wrap up, we have to mention that this energy is shared in some really fascinating ways through the law of equal partition of energy. A simple atom like argon basically just flies straight in 3 directions, X, Y, and Z. It has 3 translational degrees of freedom. But diatomic molecules, like the oxygen we breathe, they look like tiny dumbbells. So they don't just fly straight, they can actually twirl and spin like tiny dancers in the air. That adds independent axes of rotation, putting extra rotational energy into the mix, but nature ensures that the energy is always distributed perfectly equally among all the ways they can possibly move. So keeping this wonderfully hidden, chaotic realm in mind, we're going to leave you with one final kind of mind-bending question to ponder. If every solid, liquid, and gas is made of atoms in perpetual motion, and if temperature itself is simply a measure of that incessant, energetic, microscopic dancing, is anything in our entire universe ever truly perfectly still? The kinetic theory suggests that wherever there is temperature, there's a hidden symphony of motion. Thanks for joining us for this explainer, and keep questioning the universe around you.